Okay, welcome to System Devices 1, Week 8 review, what you should know by the end of the week. Okay, so this week we looked at our Simple CPU version 1D, and the aim here is to remove the limitations of our Simple CPU version 1A, so get rid of that self-modifying code, and generally improve the processing performance of our system. Okay, so the first thing we did was increase the size of our memory, so we went to a 12-bit address bus, so we could address 4096 memory locations, expanded that. We also added a register file, so we added 4 general purpose registers, so R, A, B, C and D, and expanded their data width to 16 bits to allow us to represent larger values. And because we added a register file, we then had to add a status register so we could identify what was the outcome of the last arithmetic or logical operation, so we added some status bits. So in addition to the 0 flag, we have now a carry overflow and a positive and a negative flag, allowing us to add a wider range of conditional jump instructions. A side effect of having more general purpose registers is it allows us to store more variables within the processor, so it minimizes the number of load and store instructions, and also allows us to have some additional addressing modes. So we can have a register addressing mode where all operands are stored in registers, and we can have a register indirect addressing mode, allowing us to store an address in a register rather than having it hard-coded within an instruction. And obviously the key advantage of having an address in a register is it allows us to scan through arrays. So we can put the base address of our array into that register, load that value and process it, and then we can just increment RB in this particular case here to get to the next element in our array. So as we added more instructions to our processor and different address modes, hopefully you can start to see the link between the processor's hardware architecture and its instruction set, and the limitations imposed upon us with a fixed length instruction format. So really do have a go back through this lecture and make sure you understand all those subtleties that exist between those various elements. Finally, we had a look at subroutines, so a method of implementing functions within your program, so the call and return mechanism. Looked at how we could implement those instructions and how we could implement that in hardware by having a hardware stack. We then had a look at a simple example. We have a series of nested subroutines and how the return addresses are stored on the call return stack. And as it says here, we'll continue that investigation in next week's lecture, where we look at how an external call return stack can be used to store our parameters and return the results to the main program. Okay, moving on to this week's lab, we looked at how we can improve our bug trap by replacing the hardwired controllers that were built in the previous 2 labs with a processor. So how we can implement the functionality in software. So the hardware needed to implement that design is based around our Simple CPU version 1A. So we've got some memory. Now we've also got some GPIO. We've got some general purpose input-output ports. For this particular solution, we're going to use port A. So we're going to use the input port to read our various switches and sensor data, and our output port to control the LED and the servo. Now the key thing to remember about these GPIO ports are that they are memory mapped. As far as the processor is concerned, all it can see is memory locations. So to access that functionality, we have to map those hardware devices into the processor's address space. So we have to assign them particular addresses. So we represent that as our memory map, so a graphical representation of our address space, starting out at address 0 and working up to address 255, so our 256 storage locations. And the devices that are mapped to those addresses are dependent on whether I do a read, as in this one here, or a write, as this one there. So an important point to remember is that the device that you'll be accessing is dependent whether you do a read or a write. So we have the read memory map and we have the write memory map. So if an instruction accesses a particular memory location, we may not be accessing the same hardware. So for example, if I was to read address FC, I will access port A's input port. But if I was to write to address FC, I'll be accessing port A's output port. Now the processor doesn't know anything about that. All it knows is it's writing to address FC. So this decision about what memory device should be enabled or disabled for a particular address is determined by our address decoder logic. So you can see we have 3 things in the address space. We have our main memory, we have port B, and we have port A. So each one of these needs to be enabled for a particular address range. So for our main memory, our random access memory, this will be enabled from address range from 0 to FB. Our port A will be enabled from FC and FD, and our port B will be enabled from FE to FF. So for each memory transaction, for example at load and store, the address will be placed on the address bus. This will be decoded by a block of hardware here, and we will have an enable line going to each of these hardware elements, turning it on for a particular address range. Also, each of these components can tell whether the processor is doing a load or a store by looking at the control bus, so looking at the RAM write enable signal. So when that is a 1, we know we are doing a write, and when that is a 0, we know the processor is doing a read. Again, a key point to note here, in our previous examples we had just the processor and some memory, then the data out bus of our memory was connected directly to the data in bus of the processor. But now we've got 3 different peripheral devices mapped into the address space, we need to select between them. So when we do a read, obviously we need to select the data out bus of the particular component being enabled. So we have the data out bus for port A, the data out bus for port B, and the data out bus for the memory. And you can see that goes into a multiplexer. And again, which particular data bus I read or connect to the data in bus of the processor is determined by the address that I am accessing. So again, you can see that is controlled by our address decoder. So a key thing to make sure that you understand is, can you see how these address maps are realized by the address decoder logic? And that logic is shown here. So the address bus from the processor, it comes in here, is decoded by this logic, and obviously it will produce a 1 hot value. So you'll only have a 1 on one of these outputs, enabling either the memory, port A, or port B. So the hardware needed to implement the general purpose input output port, it's very simple. The output port is just a register. So inside here I will have 8 flip-flops. And the key thing here is that the data coming from the processor, so the data stored in the accumulator, is written onto the data out bus of the processor, which is then connected to the data in bus of our general purpose input output port. So these flip-flops, their outputs are connected to wires in the outside world. So the Q outputs of the flip-flops driving this output of this register are connected to wires in the outside world. And we're only using 2 of them in this particular example. We're only using bit 0, which is connected to the servo to control the servo, and bit 1, which is connected to the LED to turn the LED on and off. So this register here is updated when its associated chip enable line goes high, so chip enable 0 from the address decoder logic, and when I'm doing a write. So if I'm doing a store instruction at address FC, for example, for port A, both of these signals will be a 1, enabling this register, storing the data that is on the data bus from the accumulator into this output port, driving those bits out into the real world. So now the data out bus of our general purpose input output port is driven by this multiplexer, and this allows me to select either the output port's value or the input port value. And you can see that again if we look at this address space. So you can see if I was to read address FC, I will read the input port value, so my switches and my sensors. And if I was to read to address FD, I will read the data stored on the output port. So that functionality is implemented by that multiplexer, and that's controlled by address line 0. So if you look at address FC, then obviously address bit 0 will be a 0 for the C. So that will select the 0 input. So I'll read the input port's value. I'll read the signals coming in on those wires in the outside world. If I was to read FD, then obviously A0 is a 1, so I'll select the 1 input, and that will select the output of my output register. And again, I'll drive those values onto the data bus, and they will be read by the processor, so when I execute a load instruction. Now each of the input and the output ports are 8 bits, and connected to those bits are the signals you see here. So for the input port, we have the push button, we have the sensors, the toggle switch, and our 1 Hz oscillator we used in the previous lab to control our binary counter. Bits 5, 6 and 7 are unused and will be set to the value 0. For our output port, we are only using the lower 2 bits, so bit 0 and bit 1. Bit 0 is connected to our servo, so if that's a 1, we'll drive the servo down into closed position. If bit 0 is a 0, then we will set it to the open position. Bit 1 controls the LED, so again if that is a 1 the LED is on, and if it's a 0 the LED is off. So here we have our first program, so do make sure you understand how that program works. So how do we map this high level description down into this assembler code? So to quickly go through that one, so we load into the accumulator the data stored at FC, and remember FC, if I read address FC, I will enable port A's input port. So I'll read the value, the current state of these signals into the accumulator. I then perform a bitwise and the key bit to understand here is that this operation here is implementing our if statement. So we're going to use a conditional jump instruction to select whether we close the trap or we open the trap. So this conditional jump is conditional on the accumulator being 0 or not 0. So by ANDing it with the value 1, we zero all the accumulator bits except for bit 0, which is our fire button. And that's an active low signal. So when the fire button is pressed, obviously bit 0 will be set to a 0, so by ANDing it with a 1, we make the state of the accumulator dependent on that signal. So if the fire button is a 0, then I'll jump to the fire section of the code, and if it's not 0, the fire button is not pressed, then I'll jump to this section of the code. So this section of the code here corresponds to the else statement, so where you want to turn on the LED and open the trap. So we move the value 2 into the accumulator. Remember, move accesses an immediate value. It does not read memory like a load instruction does. This just transfers the lower 8 bits, the operand field, into the accumulator. I then write that to address FC, so now I'm writing that value from the accumulator into the output port to set the desired bits, and then jump back to the start. If the trap was triggered and the fire button was pressed, then I'll jump to this section of the code. Again, I load in the value 1 into the accumulator and then store that out to address FC. So those values here will be written to the output port. So you can see if I wrote the value 2, then I have 00010, so the LED will be on and the servo will be in the open position. And if I was to write the value 1, so that would be 00001, then the servo will be in the closed position and the LED will be off. Again, the key point to note here, when I read and I write to address FC, I am not writing to RAM, I'm not writing to memory. Because if you look at this program here, you go, well, okay, I've moved the value 1 into the accumulator and I've written it to address FC. I jump back to the top here and then I load FC. Now, if this was memory, then obviously you would load the value 1, but it's not. When I write, I'm writing to the output port, and when I read, I'm reading the input port. Two different things. They just happen to be mapped to the same address. So make sure you understand that subtlety. Okay, to convert our assembly language program you saw previously into the machine code that the processor will run, we'll be using our Python assembler. So we can pass that text file to the assembler and it will generate the machine code I need. First step it does is obviously it compiles up into object files. So here we generate the intermediate files that needed to be passed to the linker. The linker will then convert those into a memory image that can be loaded into the Xilinx tools and synthesized and downloaded onto the FPGA. Obviously, before we do that, we can simulate it and we can see how our program behaves, how our program will respond to the changes in the various inputs to control the various outputs of our actuators. A key thing to note here is the delay between a sensor changing, an input changing, and an output changing, an actuator being updated. Because obviously now we're executing a program. Previously in our hardwired examples, as soon as an input changed, the output changed almost instantaneously after a few nanoseconds. But now, obviously, I have to do the fetch, decode, execute cycle. I have to read in that data, I have to process that data, and then update the output port. So you can see here, for example, here we have the fire signal. So it goes low at this point here, indicating the button has been pressed. But the output, my servo, does not change for a good few microseconds because it's executing that sequence of instructions to implement the control rules. So now there's a delay associated between the input changing and the output being updating. And that's due to the polling nature of our system. We have to poll the inputs, we have to test the inputs before we can update the outputs. In task 2, we looked at how macros could be used to make a higher level language. So we're using the M4 preprocessor. That allows us to define macros, so blocks of code that we can use within our program. So we can define a macro for a bitwise OR instruction, which can then be implemented by this macro you see here. The key thing to realize is that the macro allows you to do some pre-processing before runtime. So we can convert the parameter we're passing to our macro using these functions. And the M4 preprocessor allows you to do a series of calculations. So we can perform arithmetic or bitwise operations on those parameters to allow us to implement different functionality. So in this example here, we're passing the macro, the bitwise OR macro, the value F0. That inside the macro is represented by $1, so that's the first parameter you're passing to the macro. And then I can evaluate the calculation of that value with the bitwise exclusive OR with the constant 255, which effectively inverts all the bits in that parameter. I then cut and paste into the final program my AND and my add instruction that you can see there. So this program here is converted by the M4 preprocessor into this program here that actually is executed on the processor. So our bitwise OR is implemented using a bitwise AND and an add instruction. So again, make sure you're happy about how that is actually working. I can continue that idea. Now I can start to write a high-level language for my bug controller, so a macro compiler effectively. So here I have some high-level instructions, some macros. So I can define a macro that turns on the LED, turns off the LED, closes the trap, open the trap, and test whether the button is pressed. So now my high-level code you can see here is implemented by this series of macros. So I have a macro that says if the button is pressed, then I jump to the fire section. Otherwise, I turn off the LED, open the trap, and then jump back to the start. Obviously, that's just a machine level instruction. And again, here I can turn on the LED, close the trap, and then jump back around again. So it allows to make my code more readable, and it reduces the amount of code I have to write. So to use the M4P processor, we define our macros within a text file and then pass that to the M4P processor program combined with the assembly language program, and that will generate the assembler code that is passed to the assembler and then linked together to form the final memory image. In tasks 3, 4 and 5 we look at some more examples in a little bit more detail, giving you a little bit more practice of using this in a real world context, and those are your private study exercises for this week. So the key bit I would like to make sure you're happy with is the implementation of these high-level control rules in the assembly language syntax. So I'm just going to quickly go through how this high-level description of what a bug trap should do is realized by this program here. Okay, so we start our program off. The first thing we need to do is to reset our LED and our servo into its default positions. So I move the value 0 into the accumulator, then store that out to FC, my port A output port. So that will set the servo to a 0, so it's open, and the LED to a 0, so that will be off. I then want to see whether I'm in automatic or manual mode, so I will have to read the input port. So I load FC, so I read the input port, storing that value into the accumulator. I then perform the bitwise AND with the value 8, and what that will do is isolate the mode switch, so our toggle switch. So basically all the other values will be set to 0. Obviously if you think about the bit pattern for 8, that will be 0, 0, 0, 1. So now if the accumulator contains the value 0, I know the toggle switch is outputting a 0, so that will be automatic mode. And if it contains the value 1, I know I'm in manual mode. So I'll jump to the section of the code that implements that functionality, so I'll jump to manual. And if you look down here, that is exactly the same program we had previously. Alternatively, if it was the value 0, I'll jump now to the block of code that implements the automatic rules. So you can see these rules here. So there I need to check whether there's something in the trap and whether the bug is a large bug, in which case I stamp on it, or if it's a small bug, I just close the trap. So again, to get that sensor data, I have to read the port A input port at address FC. But remember, the sensors are active low. And to get around that one, to make them active high, what I can do is I can execute these two instructions here. So if I load the accumulator with the value FF, so set the accumulator bits to all 1, and then subtract from it the data on the input port at address FC, I will effectively invert the bits. So I'll make the sensor signals now active high. If I perform the bitwise AND with the value 6, you can see here I'm selecting just those 2 bits, so all the other bits will be set to 0, and the status of the accumulator will be based upon the 2 sensor values. So if those sensor values are both 0, there's nothing in the trap, then I'll jump back to the start and the whole thing repeats. But if one or more of those sensors is triggered, I need to see whether the bug is a large bug or a small bug. So if I subtract the value 6 and it produces a 0 result, I know that both of these sensors are outputting a 1. And again, remember, I've inverted these bits, so now they're active high. So if they're both set, that means it's a large bug. So if I subtract 6, that will produce a 0 result. So I jump to large to implement my stamping behavior. If it's not large, and it must be small, so I will fall through here if it's not containing the value 6. That is, if just one of the sensors is triggered. So I'll move the value 1 into the accumulator and I'll write that out to the output port. So now the value 1 will be stored to the output port, setting the servo into the closed position and turning off the LED. If the bug was large, and I'll jump to this section here, now I'll move the value 0 into the accumulator, update the output port, so the trap will be open and the LED will be off. I then read the input port again to see if the bug is still in the trap. Again, I AND it with the value 6 to isolate those 2 sensor bits and test to see if they contain a non-zero value. So remember, now I have not inverted the bits, so now these sensor values are active low. So if the accumulator contains a non-zero value, then one of these sensors must be untriggered, so therefore it will exit this loop and continue with its normal behavior. But if both sensors are triggered, we've got a large bug in the trap, then the result will be 0, so I'll pass through this into this delay loop. So to implement the stamping behavior, also I need to close a trap, wait for a certain amount of time, then open a trap, wait a certain amount of time, and then close it again. So to implement that time delay, I could use a software delay loop as mentioned in the lab script, or I can use the oscillator input coming from my 1 Hz clock. So this bit here connected to my input port will be changing every half a second. So it'll be in the low state for half a second and it'll be in the high state for half a second. And I can use that to control my trap. So again, I read the input port. Now I select the oscillator input by ANDing it with the hexadecimal value 10. So obviously that will be the lower nibble will be all zeros and the first bit of the high nibble will be a 1, isolating that input. So if that is the value 0, then I'll stay in this loop until it goes to a 1. When it does go to a 1, I will then update the trap to the closed position by loading a 1 into the accumulator and storing that out to the output port. And again, I will read in the input port and wait until that signal changes back to a 0. So again, read it in and it with 10 to isolate that signal. If it's a 1, then I stay in this loop waiting for it to change to a 0. And when it does, I will jump back round to beginning and repeat that process. So if the bug stays in the trap and it doesn't get smaller because I repeatedly stamp on it, or it does not escape, then I'll repeatedly stamp on it until the bug disappears. And as I said previously, this bottom half where I have the manual mode, that's the same as last time effectively. So again, I will read the input port, test to see if the fire button is pressed. If it has been pressed, I will turn on the LED and close the trap. Or alternatively, I will turn on the LED and open the trap, because if I'm in manual mode, the LED indicates my status. So LED is on for manual mode and off for automatic. Fingers crossed that made sense. If you have any confusion about how we map this high-level code into the assembler, do give me a shout and I'm happy to chat through it. Finally, we have this week's workshop. So again, a nice easy one to start off. What are those components within that block diagram? And then we have another example looking at how we can map high-level functionality down into an assembly language program. So previously when we've done multiplication, we've done it using through repeated addition. Now obviously repeated addition is very software inefficient. Obviously imagine you multiplying 100 by 100, you have to add 100 to itself 100 times. That's a lot of processing. So in reality what we would do is a shift and add. So we look at the multiplier bits and where there's a 1, we add that multiplicand to our shifted result, as shown by this block diagram. So that effectively reduces the number of operations that we need to do down to the number of bits in the multiplier. This algorithm is described by this flowchart. In this flowchart we can see the RTL descriptions that are happening at each stage, describing how that multiplication process is performed. So look at this flowchart and then convert that into an assembly language implementation for that algorithm. As always, we have our robot cockroach. If you're not building one this term, then you can skip over that one. And finally, we have our open exam preparation, where we implement one of the questions in a CPU Sim version 1A format. So for this one here, we're going to add our rotate instruction to our system. So I've expanded the multiplexer within the ALU to have an additional input, so I can put my rotate component I designed previously into that position, and I need to modify the assembler to allow us to add that to our program, to allow us to write a program with that new instruction. So see if you can have a go at that one. Have a look at the Python assembler, add that one to the system, and fingers crossed, touch wood, you will then be able to execute this program that you see here. Okay, I think that's where I'll leave it for this week. Next week is the final week, so I will see you for that lab and lecture.